Pictured here is an artist's representation of the detected dark matter around the constellation of Cygnus. However, dark matter can't actually be detected by normal means, and scientists only know of it because of its gravitational effect on the matter around it. Furthermore, there are theories that not only is there dark matter, but there is also a dark energy that is undetectable, but is forcing the universe apart. Dark energy is purely theoretical, but dark matter has a detectable candidate in the form of neutrinos. Neutrinos are small, nearly massless particles that don't interact with much due to their neutral charge. They are constantly streaming through the universe at the speed of light. In fact, trillions of neutrinos pass through the human body every second. But just what are these things, and what does dark matter have to do with us? Come along and enjoy the journey through the universe and the mysteries that it holds. The first question, of course, that must be asked is this. What is dark matter? Well, the definition of dark matter is this. Matter that does not give off or reflect detectable electromagnetic radiation. The radiant energy that includes visible light, radio waves, infrared radiation, X-rays, and other stuff. Although dark matter is practically invisible, astrophysicists have determined its existence by detecting its gravitational interaction with matter that does give off detectable electromagnetic radiation, such as stars, galaxies, and clusters of galaxies. So, that being said, the next question might be, just who thought up this crazy idea? The idea was first suggested in the early 20th century by a Swiss-American astronomer named Fritz Zwicky. However, since most scientists didn't have theories that as esoteric as dark matter, it wasn't accepted very much. However, it did begin taking hold about 1970 due to the work of the American astronomer Vera Rubin. So, dark matter has a bit of history behind it, though it's still been a hot subject for only about 35 to 40 years. It was determined by scientists that 90% of all matter in the universe is dark matter. So we want to know what it is to better understand our universe if so much of it is stuff we can't detect. So we put it into two broad categories, hot dark matter and cold dark matter, which is the stuff that we really can't detect at all except for the gravity. Cold dark matter could be made up of any number of things. It could be made up of machos, like black holes, neutron stars, things like that, but there can't be too many of those, so that would still account for a lot of matter. There could be things like neutrinos, just a lot of barely interacting matter that's massive. Those would be called WIMPs, or weakly interacting massive particles, but can't be too many of those, or we can't find them. Hot dark matter's definition is dark matter that's moving at about the speed of light. Neutrinos fall into this category because they have some mass. They are pretty much neutral to every other particle that exists because of their lack of charge. And, well, they have a tiny, tiny bit of mass, so they can move at the speed of light. Neutrinos are very commonplace in the universe because of the fact they're formed from the sun, reactions in our atmosphere with cosmic rays. They're formed all the time due to fusion reactions and other reactions that, well, release energy. Neutrinos speed off. They don't stick around very long. They go through the speed of light, pass through everything, but they can't really account for all the dark matter. Anyway, neutrinos come in three flavors: electron neutrinos, tau neutrinos, and muon neutrinos. Muon neutrinos are the heaviest by a small margin, and electron are the lightest by, once again, a small margin. Neutrinos are quite an interesting particle because, for one, we can detect them indirectly. We detect them by when they occasionally do react with things because, after all, they're running through the universe. If they run into something, given the fact they have mass, they will knock it out. That happens in water occasionally, in pure water. So, detectors were made up that were made out of pure water. One such is in Japan. The Super Kamiokande experiment in Japan is basically a 10,000 gallon jug of pure water that is observed to watch a neutrino interact, which is very rare, but a neutrino interact with particles in the water. When neutrinos interact with matter and produce a charged particle, the initial speed of the neutrino gives the new charged particle enough energy to move off nearly as quickly as the neutrino came in. Neutrinos always move at the speed in which light travels in a vacuum, no matter what material they travel through. The speed of light in water is slightly slower than the speed of light in a vacuum, so the charged particle initially moves faster than light does in water or ice, therefore creating a flash of light. If you want to learn more about neutrinos, because there's way too much information to be presented here, then go to encarta.msn.com and search under neutrinos. Google also works, but Encarta is a valid source. Now onto the final topic, dark energy. This is also the smallest topic due to its theoretical nature. Dark energy was only discovered about 10 years ago, when two independent teams of astronomers were searching for distant supernovae, hoping to measure at the rate at which the expansion of the universe was slowing down. They were shocked. The observations showed the opposite. The expansion was speeding up. In fact, the universe started to accelerate long ago, sometime in the last 10 billion years. Like detectives, cosmologists around the world have built up a description of dark energy. It accounts for 2/3 of the cosmic energy density. It's gravitationally repulsive. It does not appear to cluster in galaxies, and it's stretching space-time apart. The reason it goes by dark energy is because we have no idea. Some theorists think it's the cosmological constant, which certainly fits the accelerating expansion scenario because the cosmological constant is what causes that expansion. But do we really know what it is? The answer is really not. It's still being discovered, so if anybody is high and minded and when they get to graduate school and it's still not discovered, hit us up because we want to know what it is. It could be anything. It's an energy that is not very well known. It's highly theoretical, and without getting into extreme astrophysics, which is something that is really not required right now, I can't really describe it to you properly. So I'll just leave it at that. That's what dark energy is. And now we will go to the credits. Thank you for listening. And be sure to research this stuff. It's really interesting, trust me.